guess this is the right place. Wait, it's not working.
Can we come?
This has to be here. Yeah. Okay. Oh, let me see. Yes, thank you.
Hello, everyone. Welcome to this second seminar of this morning session on PDEs. So the speaker is Professor Diego Córdoba from ICMAT, Institute of Mathematical Sciences in Madrid, Spain. He's an expert in analysis, partial differential equations, and fluid mechanics. And for today, he's going to talk about finite time singularities for incompressible fluids. Please join me in welcoming Professor.
All right, thank you very much for an introduction. And yes, what I'm going to talk about is finite time singularities, in particular for the incompressible 3D Euler equations. And the goal of this talk, I'm going to focus on those singularities that happen in the bulk of the fluid, inside the fluid, okay? And I'm going to present three constructions of blow-up in finite time in a local well-closeness regime. And this is a joint work with Luis Martinez Zoroa, Fan Zheng, and Andrés Laín San Clemente. Okay. So I'm going to focus in 3D Euler equations. I'm going to consider the problem with no boundaries. So we are in the space, and we have a velocity field, U. There's a pressure, P. And there's an external force, F. They satisfy the momentum equation, and this is going to be an incompressible fluid. Therefore, the velocity is divergent free. And this models the dynamics of an ideal fluid with constant density and no viscosity. This is not only a nonlinear equation, but it's also a non-local equation, and that comes from the pressure. And in this talk, I'm going to consider classical solutions. So the solutions are going to satisfy the equation pointwise. And therefore, it satisfies the equation for that shows that the energy remains bounded in finite time. And in the case of no forcing, the energy is conserved. And in the case of a forcing, which is in L2, then you can guarantee that the energy remains bounded for all time. Okay, so the equations were written in 1754. But the locally wall poseness, was not due until the 1920s by Lichtenstein and Gunther, that they show that the problem is locally well posed in Helder spaces, Ck alpha, for k an integer bigger or equal to 1, and alpha has to be strictly in between 0 and 1. Okay? The case alpha equal to 0, this is not locally well posed, and that's due to the non-locality of the problem. And this was solved by Bourgain and Dongli 10 years ago. But if your initial data is in this Helder space Ck alpha, and the force is uniformly bounded in that space, then you can guarantee that there's a solution for a short time, and that time of existence depends on the initial data and on the bound of the force, the Ck alpha bound. Okay. And later in the 50s, And in the 70s, Evin and Marsden extended the local world postness to solvable spaces. HS for S has to be bigger than the dimension divided by 2 plus 1. And initially it was done in a compact domain, and then Kato extended to RA. Okay, so the question I'm considering is if we are in one of these local world postness regimes, can we continue the solution for all time, or there is a singularity in finite time? Of course, the force, if there's a blow-up, it cannot be due to the force. So the force has to remain in the local world postness regime. Okay? So if the force is uniformly bounded CK alpha or in HS, and your initial data is in the same space, then you can guarantee that there's a solution for a short time, and the problem is to know if there's a blow-up in finite time. And there's a criterion, blow-up criterion, for if your initial data and your force are in this world postness regimes, and in order to have a singularity, this integral has to diverge. So the velocity has to fail to be in C1 and has to grow very fast at the time of the blow-up. So the integral of the L infinity norm of the gradient of U blows up. Okay? And this is a necessary condition no matter how big K is, for example, or S is. This has to happen. Okay, so a very important quantity in fluids in this problem of blow-up is the vorticity. The vorticity is the curl of the velocity, and what measures is how fast the velocity rotates. One can write the equations in terms of the vorticity itself. You take the curl of the equation, then since the pressure disappears, because you have the gradient of the pressure, and that term disappears, and you have an equation for the vorticity in terms of the vorticity and the velocity itself. But the velocity can be written as an integral operator with respect to the vorticity by Beer-Savart law, and it has this form. So the equation is just written in terms of the vorticity. This is in 3D, but in 2D, there's a cancellation on one of the nonlinear terms, and this term, which is quadratic, in 2 dimensions is not there. And due to this cancellation, the vorticity in 2 dimensions, let's say there's no force, is conserved in time, but in 3 dimensions, this stretching term, which suggests, because this gradient of U is of the same order of the vorticity, it's a single integral operator with respect to the vorticity, this suggests that maybe there is a singularity in 3D. So maybe the vorticity blows up in finite time. And what is fighting against the singularity is the incompressibility of the velocity. Okay, so in the 1930s, Wollibner and Helder proved that in dimension 2, taking advantage of this conservation of the vorticity, that in 2 dimensions there are no singularities. It remains bounded for all time. If you're start in one of these local world postness spaces. There's but in 2 dimensions, you don't have singularities, but the solution may grow in time. And one can get an upper bound of how fast the gradient of the vorticity grows. And that's bounded by a double exponential bound in time. And a big open problem is to know if this is an optimal bound. Are there solutions that grow as a double exponential? And 10 years ago, Sasha Kiselev and Vladimir Zverak proved that yes, there are solutions in the case of a bounded domain, in the case of a disk. you can prove that there's solutions that grow as a double exponential. But in the plane, it's still an big open problem. Okay, Bill Cato and Maida in the 80s, they improved the blowout criteria, and they obtained that instead of looking at the full gradient of the velocity, you can just look at the vorticity, the infinity of the vorticity. So if that quantity remains bounded, then you have global existence. If there's a singularity, that quantity has to blow up very fast, such that the integral in time diverges as t goes to the time of the blow-up. So this is consistent with the 2 dimensions. The vorticity does not grow. There's no blow-up for 2D. But in 3D, one has to look at the vorticity. And then there's another criterion by Peter Constantine, Charles Pfefferman, and Andrew Maida in the 90s, where it suggests instead of looking at the L infinity norm of the vorticity, look at the direction field of the vorticity. If this direction field remains Lipschitz, then you don't have a singularity. It has to do wild things, the direction, in order for a singularity to happen. Okay, so before I enter on the finite time singularity, let me describe what is isosymmetric flow. An isosymmetric flow is when you pass to polar coordinates and you look at the radial component of the velocity, the angular component of the velocity, and the vertical component of the velocity, and they are independent on the angle. Those are called isosymmetric flows. And Euler equations preserves that structure. So if you start with an isosymmetric flow, it will remain an isosymmetric flow. Or if the angular vorticity, the angular velocity, is 0 initially, then it will remain 0 for all time. And those are called isosymmetric flows without swirl. So we have 3 types of solutions. Isosymmetric flows without swirl, isosymmetric flows with swirl, and non-isosymmetric flows. Okay, so in the 80s, we got this toy, which are the computers. And since we can simulate fluids, and there has been a huge attempt since the 80s to find a singularity for 3D Euler equations. And there have been many candidates. And these candidates, as the power of the computers were improving, these candidates will disappear, will be shown to be wrong, but not good candidates. Until 2014, Luo and Ho, they gave a simulation that suggested a singularity, and this singularity is self-similar. It's for isosymmetric flows with swirl. But the singularity happens at the boundary. But this is a singularity. Okay? This was a numerical simulation. Following this simulation, Tarek El-Hindi and Inji Zhong in 2019 showed that if the boundary has a corner and you start with a fluid in C1 alpha, this is a local well-posed regime, then there's a singularity, and the singularity is self-similar and it happens at the boundary. And this alpha is very small, but it's in the local well-posed regime. And this is a proof, a rigorous proof. Then, 2021, Chen and Tom Ho, they proved the same result, a finite time singularity, self-similar, happens at the boundary, but now the solutions, the initial data or the solutions are C infinity. And the singularity and the solution stops being in, it's C1 alpha, but the boundary, so I got ahead. And the boundary is smooth, and the solutions are C1 alpha, and alpha is very small. So they improve the regularity of the boundary with respect to El-Hindi and Jiho. In 2023, smooth boundary and now smooth solutions. And they prove that there's a blow-up, self-similar, and the blow-up happens at the boundary. And this is a computer system proof. They need the computer to do this, but it's a rigorous proof. They use interval arithmetics, and they need the computer to get the estimates. Okay, so now the question is, can we get a singularity but inside the fluid, not in the boundary, okay? In the bulk of the fluid. So in this attempt, Tom Ho and Ho and Huang, they published potential candidates for a singularity where the singularity happens inside the fluid. These are numerical simulations. Here, the strategy of Ho and his collaborators is to do a computer system proof. And in order to do that, they need a very good candidate, and to show that nearby that candidate, which is a numerical simulation, you actually have an actual solution of Euler equations that has the same behavior as your numerical simulation. Okay? That's the strategy of their proof. So to have a good candidate is crucial to be able to do a computer system proof. In what I understand is that these two results are not good enough, they're not close enough to a solution of Euler to be able to do a computer system proof. So the group of Tristan Buckmaster, Javier Gomez Serrano, and collaborators, they publish a paper and where they are using machine learning, AI, to find this candidate for a blow-up in order to do a computer system proof. Okay. So there's a big race in order to do this, and eventually, once they find the good candidate, they have the power and they have the knowledge to cook up a finite time singularity. Okay. In the meantime, let me tell you what can we do with pencil and paper. Okay. So El Hindi in 2021 proved the first blow-up for Euler equations when the singularity happens in the fluid. This blow-up is for self-similar, is for isosymmetric flows, but the surprise is that it's done for isosymmetric flows without swirl. He proved a blow-up for solutions or initial data and C1 alpha. This alpha is very small. And the force is also C1 alpha. So it's in the local well-Posner regime. Finite energy, and it's a legitimate blow-up, and it's the first blow-up. Okay. These blow-ups are self-similar, and they are exact self-similar. He proved without force. He actually proved that they are exact self-similar, and what happens with these solutions is that they don't decay sufficiently fast at infinity, so they're not in L2. But if you add the force, you can make the solutions decay sufficiently fast at infinity. They are in L2, and the force will be in the same space as the initial data. Okay, in another paper, Hindi team up with Bull and Masmoudi, they were able to do a stability analysis around this self-similar blow-up, and they are able to get rid of the force. For force equal to 0, they prove that there are blow-up for isosymmetric without swirl solutions in C1 alpha. Alpha is very small, very, very small, but it's in the local well-Posner regime. And they are self-similar. In this case, they're asymptotically self-similar. Okay, so these solutions Away from the axis, there's C infinity. But nearby the axis, there's C1 alpha. What I was saying that if this was done in isosymmetric flows without Shrill is, and this was a surprise, is that it was known by Ukowski and Judovic and then Chin that if the regularity of the solution is C1 1/3 or more regular, then you have global existence. But if you are between your C1 alpha with alpha between 0 and 1/3, was not known. And Hindi proved that if alpha is very small, there's a blow-up. And 2 years later, in 2023, Hindi, in collaboration with Pasqualato, they obtained another blow-up, now in the case of isosymmetric flows with Shrill. The solutions are C1 alpha. Alpha is very small, but it's in the local well postness regime. There's no force. Force is equal to 0. And they are self-similar, or asymptotically self-similar. Okay? Okay. So we propose a different way. These two blow-up scenarios are self-similar. So you make a change of variables, self-similar change of variables. You take it to your new domain is independent of time. You prove that there's a solution there, and the blow-up is due to this change of self-similar variables. Okay? And we propose a different way. We propose a cascade of vortex layers accumulating in a point where the singularity happens. Okay, the construction for a blow-up of this type has two steps. One is to find the mechanism in which the solution is growing. You have norm inflation. And this mechanism consists in the following. You have vortex layers. What is a vortex layer? A vortex layer is a compactly supported vorticity with certain regularity. It can be CK alpha or it can be C infinity. And you have another vortex layer with a smaller compact support, closer to the point where it's going to blow up. And the growth of this smaller, the next layer is due to the velocity generated by the previous layer. Okay? And if you look at the evolution of the dynamics of this layer, if the self-interactions needs to be small, and the interactions with the layers, the next layers, has to be also small. The main growth comes from the previous layer. That's the point. Okay? Now, once we have this, we are going to place infinite of these layers accumulating in one point. And that generates the blow-up. Okay, so following this general idea, we are able to cook up 3 scenarios to prove 3 blow-ups for Euler equations in the local well porousness regime. The first one has to do with the same scenario as Hindi. Self-similar and asymmetric flows without Shrill. Our initial data is going to be smooth in L2. It's smooth everywhere except at the origin. And at the origin, it's going to be C1 alpha. And that's where it's going to blow up. And our alpha is going to be also small. Right? And here, our force is 0. And then the solution blows up in finite time. Okay? The second scenario, yes. The vorticity goes like 1 over t. Yes, yes. But each scenario, they go at different speeds. It depends on the nature of the blowup. I'll give more details. No. Okay, the second result is for solutions that are non-isosymmetric. These are non-isosymmetric. The velocity, the initial is going to be c infinity in L2. But now the force, there's going to be a force, and the force is going to be C1 1/2 minus epsilon. Okay, so it's more regular than the C1 alpha of previous, because these alphas are very, very small. So this has some higher regularity. Bigger than 1/3. But these are, exactly, I was going to go over that, but they go beyond the threshold of isosymmetric flows without shrill. Okay, and the third blow-up, which we did not post it in the archives yet, will sometime after the summer, but I will explain how the scenario looks like, is isosymmetric flows with shrill. And these are initial data, C infinity, L2, and the force now is C1 square root of 4 divided by 3 minus 1. This is like 1 over 10. Okay? Okay, so the three scenarios, they have different regularity. And ones are isosymmetric, others are not, with shrill, without shrill. They follow the same general idea of building this cascade of layers, but they have completely different structure, geometry. The blow-up rates are different. So in the case, this goes like 1 over t, but this goes like faster than any polynomial. Okay, and this one goes like a polynomial, bigger than 2. And the layers, for example, the layers, how we cook up the layers, here all the layers are placed from the beginning, and they're disjoint. Here, the layers appear as time evolves. Okay? And they're not disjoint. They're inside, one layer is inside the other. The three of them have been, yes. 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 But the force is not smooth. So it's not there, okay? Okay, so this is a property of the solution we construct, okay? But one should look at the minimum regularity of both of them. For example, here, the regularity of the force is infinity, right? But the solution is C1 alpha. But they are all in the local well-posed regime. So the goal is to cook up a scenario to increase your force to C infinity. Can we do that? No, that's if you add viscosity. That's if you add viscosity. Yes? Yeah, they appear in time. Okay. Okay. The force, yes, one can think about that, yes. But why we can get rid of the force here is that we can go, here we can go backwards in time from the singularity. And here the constructions goes forward in time. Okay? If one can cook up a scenario with C infinity force, maybe there's a way to go backwards in time and get rid of the force. But this is speculations. Yeah. They blow up. They go like this one goes faster than any polynomial. One divided by t to the power is 1/t. Yes, exactly. Okay, so let me explain the three scenarios to see, so you see the how we cook them. So this is the one without swirl. It goes, it's smooth everywhere except at the origin. It's C1 alpha, in the origin is C1 alpha. Here there's no force. And the vorticity goes here like 1/t. And we are not using self-similar variables. And I'll explain how we cooked up them. And we improved the regularity of El Hindi. But recent work by Chen, he showed that using part of our ideas and using the construction of El Hindi, he showed that one can construct a self-similar blow-up where there is infinity everywhere except at the earth. Okay? 1/t, and they remain open. Both alphas, El Hindi and ours, are very small. We're talking about 1/10 to the 6, this big. Okay? And it's not worth it comparing one with another. And now there's an open problem to see if we can get to the 1/3 threshold. We go beyond the 1/3, but with non-isosymmetric flows. Okay, so how is the construction? So we are in this isosymmetric flow, and we're going to build and take vortex layers. They're going to be disjoint. We place them, and with the correct signs and symmetric one from the other, in order to have a hyperbolic saddle in the origin. The three scenarios, the growth is due to the hyperbolic saddle, to a hyperbolic saddle, the three of them. Okay? The first two, this one and the non-isosymmetric, the point where it blows up is at the origin, and there the saddle does not move. Okay? So the third construction, the hyperbolic saddle moves in time. It's more complicated. And the way it moves, it satisfies the movement of a pendulum. It's incredible. Okay? Okay, so let's say I place these layers. Okay? And I'm going to each layer, the nth layer, I'm going to think of it as the profile times the height of the layer. I'm going to assume that the profile does not change much in time. And what we realize is that the evolution of the layer, of the height of the layer, satisfies this ODE, where the growth depends on the previous layer. But the self-interaction of it with itself is small, and the self-interaction with the layers after n is small. You have infinitely many of them. Yes, we have to, and it's a cascade, and it goes. We put infinite of them, and collapsing in one point. This is an ODE that we can solve explicitly. We can take, let's say that the blow up happens at time 0. Let's take the height at time 0 to be a number to the power n. Since we have a blow up and the vorticity has to blow up, and these are the heights of the layers, we better take a equal to 1. So when we take infinity of them, the vorticity blows up at 0. Well, this is an ODE that you can solve, and you can go backwards in time. And if you solve, instantly, the height of the layer decays to 0 exponentially. So at time of the blow up, it blows up, it goes to infinity, as n tends to infinity, and if you go a little bit short time right before 0, your height tends to 0. Okay? Okay, so now, how do we cook up the blow up? We truncate, we have an infinite of these layers. Let's truncate up to capital N layer. And let's take that our layers look like this. And what we're going to do is prove a local existence theorem going backwards in time from the singularity. Okay? We take advantage of this. We get local world closeness and a priori energy estimates, depending on capital N. And what we show is that at n, capital N tends to infinity, the solution the omega n converges to a solution to the equation. Okay? So the bounds we get are uniformly bounded with respect to capital N. The solution we get is going to be Helder continuous before the blow up. And at the time of the blow up, it blows up, and it blows up like 1 over t. And that's how we prove it. Yes? Yeah, of course, of course. But what our guess in the beginning, to get the ODE, we assume that the profile does not change much. If you assume that, you get this ODE with errors, which you can integrate. Fantastic. There we haven't proven anything. So we prove a local existence. And by proving a local existence, we're proving that the profile does not change much. Right. Yeah. We're taking this to be a solution of the problem of Euler equations. And we're proving a local existence going backwards in time. But since we got this ODE inside the equation, the singularity comes from the ODE exactly. That's why we can close the estimates uniformly with respect to capital N. Okay? Okay, so there's no what. Okay, is due to taking infinite of them, right? If you only take a finite number of them, how do we use this? The saddle point? Oh, we don't use the saddle point. The saddle point comes from the growth. It comes from the ODE. The saddle point gives you the ODE. Let's say the geometry of the solutions gives you the ODE. Exactly. In the ODE, you don't see the saddle point. Well, you see that in 0, the velocity is 0. Okay, well, it's odd. You see the oddness, but you don't see the saddle, exactly. Okay? Okay, now, the non-isosymmetric. Okay, so this is with force. There's no symmetry, and the force is in this space. Okay? As I said before, the solutions, they're not isosymmetric. In the theorem, we wrote C3, but actually, these are C infinity, but it doesn't matter. It has to have what you should look at is the less regular part. If the force has less regularity, is that what you have to look at. and the solutions for this, the gradient of u goes up, but they are in some C1 minus delta, and delta is small, but they are not C1. Okay, these solutions. Okay, so let me tell you about this construction. And this construction is, again, we're accumulating vortex layers in a point, but now the layers will appear in time. How to do this? So we introduce them sequentially in time, and let me give you a toy model. It's again a hyperbolic saddle. Here we see the hyperbolic saddle right away. And we take a vortex layer, the initial vortex layer, the background vortex layer, which has a hyperbolic saddle at the origin. Okay? So let's say near the origin has a hyperbolic saddle in the plane x1, x2. Then I'm going to take a new layer, which is, we can think about the perturbation. And we are going to look at the evolution of this layer by Euler equations, right? Okay, so here the velocity is the velocity induced by the perturbation and the velocity given by the background layer. And we have linearized, so this is an approximation. And this is just Euler equations. Okay? Let's say that our strength initial of the background layer is capital K. Okay. One thing to simplify our perturbation, I'm going to take it to be omega 1, 0, 0 to simplify things, but the vorticity has to be divergence free, so I'm making another approximation. I'm going to choose, I can choose omega 1. I'm going to choose it such a way that the interaction, well, self-interaction is small. Okay? That's one of the conditions. Okay, if that's true, I get rid of this term. I'm here. Now, this one, I can integrate explicitly. And when I integrate, and I see the evolution of omega 1 for a short time, and then I look at the solution. Okay? And the solution, I linearize, and I get a hyperbolic saddle, but now instead of the x1 and x2 plane, I'm in the x2, x3 plane. Mm-hmm. But our strength has grown exponentially. Okay? I place another perturbation. So this hyperbolic saddle will increase it again. Same way. I make sure that the self-interaction is small. I look at the evolution of the new perturbation. I look at the velocity field. I linearize. And now I have a hyperbolic saddle in the x1, x3 plane. I do the same again. Make the perturbation. Put the perturbation. I look at the evolution, and I'm back to the hyperbolic saddle x1, x2. But the strength of my vorticity has grown e to the e to the e to the e. Okay? So, the goal is to do this an infinite number of times. I made a lot of approximations. I made, for example, that the vorticity of perturbation is not divergent free. Okay? I take that account, and that I put it into the force. I have another approximation. My fluid, the hyperbolic saddle, I linearized the velocity of my background layer. Right? That's an approximation. The correction to the force. Every time I chose a layer, I look at the self-interaction. And what did I do? I chose it such that it's small. It's not exactly zero, but it's small. Smallness to the force. That's the growth. That's exactly the growth. Yes, yes, yes. You make sure that the next steps, your the main growth is due to the background layer, right? And you have to make sure that as you evolve, your new velocity, which will be your background layer, your background velocity, your layer plus the previous ones, if you want to think it like that, it can be approximated by the hyperbolic, by the linear part around zero. Okay, you put that on the force. That can be done. Now, you were going to do this an infinite number of times. You're changing planes and you're putting layers. You have you have to be careful that your force does not diverge. If it diverges, you will get a singular force, and then your singularity will not be in the local well-posed regime. Oh, because that's the structure. This is something that the solution gives us, and we have to take advantage of that. Because I put a new layer, right? I look at the evolution. I look at the new velocity field, and there is in a different plane. The hyperbolic saddle is in a different plane. It goes from x1, x2 to x2, x3. I don't care. In my next layer, I'm going to put it in the plane where this hyperbolic saddle in x2, x3 grows. I wait for a short time, and I look at the new velocity field, and now I have a hyperbolic saddle in the plane x1, x3. I take another layer, I look at the evolution, and then I'm back to the plane x1, x2. And I iterate this an infinite number of times. Okay? The main goal is to get the force to be sufficiently regular and to have a blow up. You maybe have it too regular and you do not blow up. You're growing very fast, exponentials. So you better, this structure, this geometric structure, you better be very precise and that there's this cancellation in order to make the force regular. And of course, you have to make sure that as time evolves, everything that you consider are maintained in time. Okay? And here is the building block of one of the layers. This is the strength. These are cutoff functions. We are taking the compactly supported. We're going to be sinusoidal components. So we need to have cutoffs. All right? This is the building block. Now, I look at the Biot-Savart law, and it gives me this, if we're in the nth iteration, this gives me a hyperbolic saddle in n plus 1, n plus 2. Okay? And it grows, and since it's a hyperbolic saddle, it shrinks in one side and expands in the other. You do this for a short time. Yes? I can't hear you. But the cutoffs is to make it compactly supported. They generate, exactly, they generate error terms. The error term, no, it's you uh, you build it in such a way that the error terms will, okay, will limitate you to get a smooth forcing, for example. So the 1/2 comes from the cutoffs, the limitation of the cutoffs. Here is the strength. The, yes. Okay, so we sum infinite of these, we iterate this an infinite number of times, and that what produces the blow up. And a key point here is that actually the linearizing the hyperbolic saddle is not good enough. It breaks the structure of the solutions. So what we have to cook up is a velocity that is almost linear, and it has this the structure. If you take the velocity to be like this, each time you look at the growth, and then the structure of the whole game is preserved in time. Okay? Okay, so that's the blow up, the second blow up. How am I doing with time? I think I'm doing terribly bad.
3 minutes.
Whew. Okay, so I'm going to skip the third one. The third one is again, we are accumulating layers, okay? But now, instead of the hyperbolic saddle to be at the origin, it's going to move. And the dynamics of this is going to satisfy a pendulum. And we have to approximate that dynamics very carefully in order to have the bounds we want for the force to be sufficiently regular. Okay. Okay, so I'm going to skip all this and go to the final slide. Is can we add dissipation to the system? Dissipation is going to fight back. It's going to prevent the singularity to happen. And the answer is yes. And let's take fractional power of the Laplacian. If it was proven by Lyons that if this power is bigger than 5/2, or 5, depends on the definition, 5/2, and then you have global existence. Well, we add this, and we showed that if alpha is between 0 and 0.09, we have singularities. Okay, and the scenario we use is the one that has the higher regularity, the C1 1/2 minus epsilon. That the game of changing planes that allows us to get to 0.09, and in the local world Posner regime. Now there are two. Can we improve this? There are two ways to improve this. Getting a better scenario that allows you to have a singularity bigger than 0.09, or to improve the local world postness. The local world postness, when there's viscosity, this is not optimal. So we look at this in the literature, try to find for the fractional Laplacian a local world postness for Euler equation plus this dissipation, and we couldn't find it, so we cook up the best local world postness possible, and then we are able to go to 2 divided by 7. To go higher, one has to find a better blow-up scenario. And the last thing, which I finish, is can this give you a C infinity force? And the answer is yes. This strategy and give you a C infinity force. And we managed to do that for what is known as the incompressible Purus media equation, which is in 2 dimensions. You have a transport equation for density rho. You have a source. The source is C infinity, is compactly supported. And here, the incompressible Purus media, the relation between the velocity and the density is given by this double Riesz transforms. Okay, so the velocity and the density are of the same order. And for this, we prove finite time singularities, and I finish here. Thanks.
Thank you for your talk. Any questions?
So in the last result you mentioned with the infinity force, what scenario was it? I'm not sure which scenario was it, and can you tell us what is the rate of blow up?
Okay, the rate of blow up is faster than any exponential, any power. Okay, so it might be exponential, and the scenario is not due. The growth is not due to hyperbolic saddle. It's a different scenario, completely different scenario, but it's again building layers as time that appears sequentially in time. Okay? It's the same accumulation of a cascade of vortex layers.
Can you do it to the torus with periodic boundary conditions?
I will not be surprised. We haven't done it. We haven't looked at it. These are compactly supported.
It's just a clean formulation. No boundary.
No boundary. Yeah, exactly. I will be surprised if it does not work.
I think it would be nice because then
people. but these solutions, if you look at the vorticity equation, they are compactly supported in the vorticity formulation.
Yeah,
what happens is that when you go back to the velocity, then the velocity is not going to be compactly supported, it's going to be an out.
Other questions?
You mentioned this approach by Gomez Serrano to the Navier-Stokes problem. And is it possible to take your proof and put it in one of these programs and see if you can see from there, or it's a black box?
Okay, so maybe I cannot. I don't know how to do it. Maybe once we understand more, or we see a more way of writing this as a general way. Each scenario are completely different.
Yes.
Yeah.
Yes.
So
Yes,
one cannot follow from the other, but maybe there's a way to cook up a way to cook up this.
So in other words, like, did Gomez Serrano ever try to find the initial solutions of try to reprove your theorem?
If he did, he didn't tell me.
Oh, that's not nice.
But I think in what they're doing, I think okay, so they are searching for self-similar blow-ups. That's what they're searching for. It's completely different. And once they capture a very good candidate for a self-similar blow-up, then they cook up this computer system proof to prove that nearby that solution, there's an actual solution of the equation. And I think they already have the strategy the way, and my personal opinion is that they're going to solve it very soon. We just have to be much faster.
Okay, that's a good point.
Other questions? So I have just a random question. There are some equations called binomial curvature flow. Are they related to this geometry? pattern that you.
I don't know.
Okay.
I don't know. I don't know.
Okay.
Maybe.
Thank you for your talk. Let's thank the speaker.
Thank you.